There are black holes that stretch the imagination. And then there are black holes that stretch the limits of physics. In a distant galaxy cluster known as the Phoenix Cluster, catalogued as SBT CLJ 2344-4243, astronomers discovered one of the most extreme environments ever observed in the universe. At its center lies a giant elliptical galaxy. And at the heart of that galaxy, there appears to be an ultramassive black hole, commonly referred to as PhoenixA. Estimates suggest it may contain hundreds of billions of times the mass of our Sun. Not millions, not a few billion, but possibly hundreds of billions. If that upper range is correct, it would place PhoenixA among the most massive black holes ever identified. But what makes it truly fascinating is not just its size. It is the environment around it. The Phoenix Cluster is not quiet. It is violent. It's luminous. It is actively forming stars at an extraordinary rate. And somehow at the center of all of it, gravity is in control. To understand PhoenixA, we need perspective. At the center of our Milky Way lies Sagittarius A, a black hole with about 3 million solar masses. Meanwhile, in the center of the galaxy M87, astronomers find a black hole weighing about 6.5 billion suns. The one famously imaged by the Event Horizon Telescope Collaboration, or abbreviated EHTC. Those are already enormous. But ultramassive black holes are a different category. These are black holes exceeding 10 billion solar masses. PhoenixA is believed to fall into this category. If its mass is closer to the higher estimates, it would rival or even exceed some of the most massive known black holes, such as the one in galaxy IC 1101. And here's what makes that extraordinary. Black holes grow, but they don't grow easily to that scale. There are natural limits, or at least we thought there were. The Phoenix Cluster is located about 5.7 billion light-years away. That means when we observe it, we are looking at a time when Earth was roughly half its current age. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds of galaxies, vast clouds of superheated gas, dark matter halos holding everything together. The Phoenix Cluster stands out because of its extreme properties. Its central galaxy is producing stars at a rate hundreds of times greater than the Milky Way. That's unusual. In most large galaxy clusters, star formation slows down because the central black hole injects energy into the surrounding gas, preventing it from cooling. This process is called active galactic nucleus feedback, or abbreviated AGN feedback. It acts like a thermostat. Too much cooling leads to star formation. The black hole turns on. Jets heat the gas. Cooling slows. Balance is restored. But in the Phoenix Cluster, that balance seems imperfect. Cooling is happening rapidly. Star formation is intense. And the central black hole is active. It's a system pushing boundaries. There are two main growth mechanisms for supermassive black holes. One, accretion, pulling in gas and dust. Second, mergers, combining with other black holes during galaxy collisions. In dense galaxy clusters, mergers are frequent over cosmic time. Galaxies collide. Their stars mostly pass by one another. But their central black holes eventually sink toward the center through dynamical friction. When they merge, the black hole grows. Over billions of years, this can create extremely massive central black holes. But here's the complication. The earlier the universe, the faster structures formed. So one possibility is that PhoenixA experienced a period of rapid growth in the early universe, feeding aggressively when gas was abundant. Another possibility is that repeated mergers in the cluster core steadily built it up over time. We cannot directly weigh PhoenixA the way we do closer black holes. Instead, astronomers estimate its mass based on the velocity dispersion of stars in its host galaxy, X-ray luminosity, AGN properties, scaling relations between galaxy mass and black hole mass. That means the number is an estimate, but even conservative estimates place it among the largest known. When matter falls toward a black hole, it does not simply disappear. It forms an accretion disk, a rotating structure of superheated plasma. Friction and magnetic interactions heat the material to millions of degrees. The region shines brightly in X-rays. PhoenixA powers an active galactic nucleus. That means it is in active state. It is feeding. And when it feeds, it releases enormous energy. Not from inside the black hole, but from the material just outside the event horizon. This energy can launch relativistic jets, streams of particles traveling near the speed of light. These jets can extend tens or even hundreds of thousands of light years. They inject energy into the surrounding cluster gas, and that energy shapes the evolution of the entire cluster. In this sense, PhoenixA is not just a black hole. It is an engine influencing an entire cosmic ecosystem. At some scale, we expect feedback to regulate growth. If a black hole feeds too aggressively, its output heats the surrounding gas and cuts off its own supply. This self-regulation explains why most supermassive black holes correlate with the size of their host galaxies. But PhoenixA sits near the upper edge of that relationship, which raises a question. Are we seeing the upper natural limit of black hole growth? Or are there even larger ones still undiscovered? Current cosmological models suggest there may be practical upper bounds, probably around more than 100 billion solar masses, because eventually gas supply becomes inefficient and mergers become rarer. If PhoenixA approaches that threshold, it may represent a near maximum case under known physics. If you could somehow approach PhoenixA, ignoring the obvious impossibilities, what would you notice? You would not see a hole. You would see an intensely bright central region. The accretion disk would dominate the scene. Radiation would be lethal at extreme distances. The gravitational influence would extend far beyond the event horizon. Stars in the central galaxy would orbit under its dominance. But gravity behaves the same way it does anywhere else. Even ultramassive black holes follow Einstein's equations. The difference is scale. PhoenixA matters because it tests our models. It challenges assumptions about galaxy evolution, feedback efficiency, black hole growth rates, the balance between cooling gas and AGN heating. It forces astronomers to refine simulations of large-scale structure formation. And perhaps most importantly, it reminds us that the universe does not form objects evenly. It forms extremes. Rare, powerful, difficult to explain. It's easy to call PhoenixA a monster, but the word doesn't quite fit. It is not violent for the sake of destruction. It is simply gravity operating at extraordinary scale. Billions of light years away, this ultramassive black hole continues to influence its galaxy cluster. It feeds, it radiates, it regulates, and yet, in the grand scheme of the universe, it is just one object among trillions of galaxies. Perhaps the most humbling realization is this: the universe can produce structures far beyond our everyday intuition, and we are only beginning to understand how. PhoenixA is not the end of the story. It may be a clue, a marker, pointing toward deeper physics, better models, and new discoveries waiting in the dark. The real question is not how big PhoenixA is. The real question is, what else is out there, still hidden in the data, waiting to change what we think is possible?